Okay, hello and welcome to a brand new week. So we're going to get through these slides this week, this lecture, and the next one. I have a potpourri of topics for you: searching, sorting, and complexity. The first one is going to be the most important for us for this class. The other two I'm just going to try and touch on to get you ready to potentially learn about it in detail in CSCI 41. Okay, so if you zone out during any time, definitely don't let it be this part, okay? That is what I want to say. So let us start, and let's talk about searching. So oftentimes we have an array or a vector, or just any kind of data structure. It doesn't have to look like this. It could be that linked list thing that I talked about before and that you had on your Xylab. You have things that hold stuff, and it would be nice, like, if you knew that 42 was in there somewhere, to like be able to find it. Like, where are you, 42? Tell me what index you're at. Let's search for it. Okay, that is the goal of searching, and there are many different algorithms depending on the data structure. Okay, we are going to talk about when it is a vector or an array. So it's a straight line thing. It's just a bunch of boxes right next to each other, and we're trying to look for something. Okay, so it's like we have this array / vector, and we want to see if some special value, like 42, is in it somewhere. Okay? That's the idea. So we want to know that it's, okay, at index 3. That is the hope. We want to find it there. Okay, so like we have a value that we want to search for. We can call it val to search for. I didn't give myself enough room for that. If that's 42, then we're going to go through our vector and figure out, oh yeah, it's at index 3. Or, oh, it wasn't there. Yeah? That's the goal. Okay, so if we have a vector, the easiest way to go through the whole thing, like, I don't know what the values are, the easiest way to search for something in a vector is to just try every possible index. Search the 0th one, the 1th one, the 2nd one, the 3rd one, the 4th one, all the way until you get to the end, and see if the thing that you're looking for is there. Okay, that's the easiest way to search for something. So just check every index, see if it's there, and you're checking it one by one by one, left to right. It is linear, right? You're searching in a line, right? We call it linear search for that reason. Okay, so I'm just going to show you how to code this up, linear search. This is what it'll look like. So here's the declaration. What it's going to do is it's going to return the index of the value that you want to search for inside of some vector v. Okay, that is the goal. Okay, that is what linear search will be, and we want it to give back the index if we find it. Otherwise, if we're looking for like 43 or something and it's not there, then we want to give back, we always have to give back some int. We can give back -1 as the answer, just saying that, hey, we didn't find it. Okay, this is essentially what the dot find method is doing that you know about on strings, right? That's essentially what it's doing. So yeah, linear search. This seems very simple, but it's actually the best you can do when you have no clue about what's in your array. Like, we have no clue whether or not the 42 is way here at the beginning or somewhere in the middle, or maybe even at the end. And because we have no guarantee about where these values are, we are forced to look in all of them, left to right, to see if what we want is really there, okay? Because the element we want could be anywhere. So that is linear search. It's the best you can do when you don't have any clue about what's inside the array, the order of its elements, okay? We can do better if we know about the order, so maybe think about that while I'm working on linear search. But let me copy this, and just to save me some time later, let me make this be part of a searching library, okay? If you can just allow me to do that. Let's start a searching library with a .h, a .cpp file, like searching.h, searching.cpp, and like maybe a main.cpp or something, just to actually run the code. So that's what I would like, and let's get started with that. So the very first thing I want to do is make searching.h, probably. That would make the most sense. Either that or main. So remember your header file guards, because it's a header file. So I think, did I still have it? Yeah, cool. So here's our linear search declaration. Okay, and this is what we want. And if we want to use vectors, we have to include vector. And we can't say namespace standard in a header file because that'll include it for whatever user tries to include this. So we say standard : vector, just to play it safe. And so this is the declaration of linear search. This is all the user needs to see when they want to do this. Okay, so that's our first file. And then we can go and implement this in the .cpp file. But I might as well make the main file as well first. So what we'll do in the main file is include this file, searching.h, that we made, so that we can use the stuff that's defined inside of it. For example, the linear search. Okay, and so what it does, it's going to take a vector. So let's make one of those. Vector of ints v. Let's make it just holds, I don't know, 8, 6, 7, 5, 3, 0, 9. And what we'd like to do is search for values in the vector. So like maybe we can search for, I don't know, 6. And then we can also search for, well, let's make it fancy. Let's search for 0. Let's search for 10. Okay, so one's there, one's not there. And what this should print is, let's figure it out. And then this one should print -1 because it's not there, right? So 0, 1, 2, 3, 4, 5. So it should print 5 here. And that's what we should see when we implement linear search properly. Okay, so using this as our guide, let us go and implement searching.cpp and get that linear search ready to go. So include our header file, because that will include vector for us. That's quite nice. We get that for free. Hey. And then also, we're allowed to, in the CPP file, because that's just for us, to use namespace standard. Okay, so now I've got this ready. Let's go and implement linear search. Are you ready? So what we want to do is search for, val to search for, in v, and return the index of it if we find it. Okay? If we don't find it, val to search for, then we return -1. Okay? So that is the game plan, and let us get started. So we're just going to search left to right in this vector. And we need to keep track of indices, so we can't do the fancy for blah in v without some extra work. So we might as well just say int I. Okay, so let's see. We have to search through this vector, see if our current index at I holds this value, see if we need to continue. So if v at I is equal to the val that we're looking for, then we should return I. That's the index where it is. Okay, that's all we want. I guess I should say we return the first index of it, because you might have the same thing twice in a vector, one right after another or somewhere later. We're going to give back the first index because we're searching from left to right. See that? So that's important. And then, okay, if we found it inside this loop, we will have returned something, and the function would have stopped. But if we finish the loop and don't return, that means we didn't find it. Return -1. Okay, so that is linear search. That's all. Let me show you it running, just to prove that it's working, but it really shouldn't be too bad. It's just a way of looking for stuff. Okay, so let's go and compile this now. So you say g++, remember all our files, g++ standard equals C++17, then you give it all the .cpp files, main.cpp, searching.cpp. Okay, and oops, I forgot to give the output file. Let's call it main. Okay, so now we've got a file called main that we can run, and hopefully it's going to print 5 and -1. Hey, so that, my friends, is linear search. Okay, and so that's as good as you can do when you have no clue about the arrangement of the values in the vector / array. You can do better, though. One thing that you can do is exploit a sorted array. Okay, so let me show you the argument there. If instead v looked like this, like, I don't know, 1, 7, 33, 42, 55, 87, if you were looking for, let's say, 55, that was your val to search for, what you could do, if you knew it was sorted, is, like, cut off things. If you, like, start over here, like, this is the first index you look at, and you notice that, well, it's too small to be 55, I know this is in order, you can cut off this half of the array. Do you see that? You don't ever have to look over here because you know 55 can't be there. And so very quickly you can get to the right side of the array and you can play that same game, cutting off pieces of the array, halves of it, when you know that it's not there. Okay, so this is called binary search. So there's something with 2 going on, and so we're halving things. So 1/2, I guess. This is called binary search. It all looks the same. It's still going to do the same thing in the end, but it can do it a whole lot faster because the array is sorted. Okay, so that tells us exactly where an element might be, and the way that you search for binary search in a sorted vector is like as if you were playing the guess the number game. So remember the optimal strategy for that. Let's say I am asking you to guess a number between 1 and 100 inclusive. What is the first number you should always guess if you want to be right as quick as possible? And the answer is 50, right? Because that cuts off your search space. If I tell you it's too low, then you know that number, if I say too low, then you know to look to guess between 51 and 100 now. Okay, you cut off this side over here. That's the goal. And then what's the next thing that you'll check? What's halfway between 51 and 100? 75-ish, right? You'll say 75. And that'll be in the middle of this little interval. And if I tell you that's too high, now you know you're cutting down the search space very quickly. The search space is the technical term for this. Now you know that you better search between 51 and 74. You see that? And so very, very quickly do you whittle down how many things you need to look at. I only need to look at less than 25 things now after 2 guesses. That's way less than a length 100 array. You see where I'm going with this? So that's binary search. And you just always check in the middle. That will have your search space, and that is the technical term, with each guess. So let me break that down some more with lots of words. Sorry, let me see if I can make that a little bit bigger. Okay, so here's what you want to do. If I can copy this again, here's what we want. Binary search. There we go. So let's pretend we're looking for 55. That's our val to search for. We'll just call it val. 55. And the idea is you treat it like it's a guess the number game. Your entire search space is indices 0, 1, 2, 3, 4, 5, 0 through 5 right now, okay? So, like, you think of it like indices. A low index and a high index. That's your starting number to guess and your ending number to guess. And you need to guess in the middle. See that? So, this is like your low. This is like your high. Okay, low starts out being 0, high starts out being 5. That's the length of the array. And then your first guess is in the middle. Average the numbers, 5 plus 0 over 2. Integer division, I guess, which is going to be 2, right? So the very first guess, the very first index we look at is 2. That's like the midpoint, okay? And we compare 33 to our 55 that we're trying to search for, okay? And what do we get? Well, we notice that 33 is a little too small. So what do we guess now? Like, what does our search space turn into? Same V, 1, 7, 33, 42, 55, 87. same all that, but now our search space can become this, right? This is now our new low. This is our new high. Do you see that? We've just cut off this half of the array. And then our next thing, our next midpoint, will of course be this one. And we'll find it in 2 guesses rather than linear search would take 1, 2, 3, 4, 5. And this gets really good really quickly for extra long arrays. Okay? So this is the goal. Okay, this is the strategy, and here is essentially how it works. It's going to be a loop. So you start these low indices and high indices in this way, and initially they are like this, 0 and the index of the last element. And that means, like, I don't know where this thing is, it's somewhere in this entire vector. And then repeatedly, what you're going to do is you're going to guess in the middle of low and high, because low and high will change. And after you compare the value at the midpoint, you figure out, okay, do I need to go lower or go higher? Okay, and that will update low or high. And then you know you're done. You eventually are done when low and high pass each other. Okay, if they ever pass each other, that means we couldn't find the thing. Okay, that is the last little trick. Okay, and this is really, really efficient because you cut off half the array each time you make a guess. And you'll get to it very, very quickly, no matter if you have a size 5 array or a size 5,000 array. Okay, so let me go and code up binary search now, following this guide. Okay, all this. So we got our now binary search. Oops, I wanted that. So again, standard vector v. And then we'll go and implement it. We might as well go to the main file for a second to make a nice sorted vector. What was this one? 17, 33, 42, 55, 87. Sure. This is v2, I guess. And then we can say binary search for all these values. Let's search for 55, and then we can search for 10 because it's not there. So 55 will print again. Is that the same? 0, 1, 2, 3, 4. 4 this time. Oops. That's what I wanted. Okay. And oops, this should be binary search, of course. There we go. Okay. So now that's our goal. That's where we're going. Here's what we do. We set up our low and high indices. Okay. Int low equals 0. Int high equals v.size minus 1. Our search space is initially the entire vector. Initially the entire vector. And then we need to repeatedly search for stuff. Okay, so we'll come to the condition of the while loop in a second. While something. What we do repeatedly is we look at the middle element between low and high. So int mid equals low plus high over 2. And so then we search and look there. So what are our possibilities? If the value we're looking for is bigger than the mid, well then we need to search to the right. Okay? Otherwise, else if the value that we're looking for is smaller than the mid, that means this value was like, we were looking for maybe 1 and we got to 33, we need to search over here on the left side. So let's do that. We're going to search for the, oops, search the left half, go left. And then else, what's the only other option? It wasn't big, it wasn't less, it was equal to. We found it. return the index. The index was mid. Okay, so how do we search the right half? How do we search the left half? So what this means is we need to, if we want to go right, we want to search from mid plus 1 all the way to high still. Okay? That's what we want. Okay? And for left half, that means search from low to mid minus 1. See that? Because it wasn't mid. We knew it wasn't. Oh shoot, I'm so sorry. We have to actually go into the vector at mid. Mid is an index. I'm sure you were yelling at me through the screen. So that's what it should be now. So mid is going to change, low is going to change in this first one. So low equals mid plus 1. That will make it so that the next time we check, we're in between mid plus 1 and high. So the low needed to change. And this one means the high needs to change. Because low stayed the same, we want to search from low to, now though, the new high point is mid minus 1. Okay, so that is essentially the algorithm. And then when do we stop? When did we know we've looked too much and it's not there? That is when this comes into play. If low and high ever pass each other, that means the search space is empty. And what we were looking for really wasn't there. We tried to look in between indices for what we were looking for. That's what it meant. Like, okay, it was like low was 1, high was 1, and it was 8 or something. And so it tried to put them over here and keep low the same. It messed up. It didn't find the thing. And so only when it can't find it does low ever get bigger than high. So as long as low is less than or equal to high, we're good. Okay? Okay, so that's the one key. Low and high will pass each other if the value isn't actually there. Okay? And so if we ever plop out of the loop, that means we didn't return and we didn't find it. Sad day, and we can return -1. Okay, so let me show you this working now. Let's go to main.cpp, and hopefully it will print what we're looking at. Yay, -1, negative. Oh no, let's see here. Oh, I gave it v. That'll do it. v2. There we go, 4 and -1. So what's happening is it first looks at 33. It's like, okay, I need to go to the right half. And then it makes a new low and high. And then the mid is 55. And hey, it's finally found the thing that we're looking for. Let's say that the value that we were really looking for was, I don't know, how about 43? Then low and high would both be here. High would move to here as well. We wouldn't find it, and so we'd think that we need to look higher, which means we would change low to be 1 more, and high stays the same. And that's how they pass each other, if that made sense. They only ever pass each other when you didn't find the thing. Okay? So this is very, very efficient. It's very, very nice. Much faster than linear search. That is called binary search. It cuts the array in 2, or the vector in 2 every time you make a guess, every time you take a look inside of it. So that's binary search. Please yell at me if you have any questions about this. These are two very important algorithms that I want to get across to you. And now I'm going to just give you a hint about your lab. Okay? Your next lab is about a similar concept to binary search. It's to make sure that you're getting it. So what you're going to do in your lab is calculate the square root of a number by making guesses, and you'll get twice as accurate. You'll get twice as close each time. Okay, it's very similar to binary search. So you'll make a function that looks like this. Square root takes a number and gives back the square root of x, even if it's a decimal number. And so what it's going to do is repeatedly guess. See if its guess is good enough to be the real square root. Okay, so here's what you do. Here's the graph of the square root function, right? It is, the fancy word is monotonically increasing. So it's only ever going to hit one value once. It's 1 to 1, and it's always increasing. Okay? So with that, that makes it very, very easy to check for the square root. Some weird things happen around 1, though. The issue there is, here's 1. The square root of a number less than 1 is bigger than that number, and that kind of throws things off. So this initial guess gets a bit weird, but that's the only weird thing. Everything else makes sense. So let's pretend we're searching for the square root of like 4 over here, and of course the answer is 2. But how do we figure that out? Okay, well, how do we do that? Or let's say the square root of 2 maybe, because I think I wrote that on the next slide. How do we figure out this should be 1.4 whatever? Well, you just make a guess. Okay, so your starting guess is where you think the square root should be. Okay, where should it be? And so the square root should be, well, it's somewhere between 0. Like, I don't know what square root of 2 is, but I know it's somewhere between 0 and 2. Yeah? I hope that makes sense. It's definitely going to be smaller than 2 in the end. So that's our low and high again. You see that? That's the game we play. Low and high again. I'm not sure where the square root of 2 is, but it's somewhere here. I think this is what I should be looking at. This is low, this is high, here's 2 up here. And what happens is, you're going to guess in the middle now. Okay, so the midpoint is 1. And see if that's close to the square root. How do you do that? Like, okay, our guess for the square root of 2 is 1. How do we know if that is very close to the square root of 2? Well, square it. If we really had something close to the square root of 2, that would give us back 2, right? But we got 1 back. And that means we need to guess higher. Do you see that? That's the key, okay? So you just check if you're close by squaring the middle, the mid, and seeing if it was close to the original number, okay? And close is something like this, because we're checking doubles again, remember? So you got to do like an absolute value kind of thing. See if the absolute value of mid squared is less than all that, and I shouldn't trick you into thinking this is code, because that square root of 2 doesn't really work like that, right? Let me do this. There. That's what you should be checking. Once you find a mid that is close enough, you're done, okay? Otherwise, if it was too low or too high, you kind of do the same thing, but there's no +1 or -1 anymore. So here, for example, the low needs to change. Low needs to become the old mid, because we want to guess higher. So now here's our new low. See that? And now the mid, our guess for the square root of 2, is now 1.5. You see that? And so you do 1.5 squared, and notice that it's a little bit bigger than 2, right? So that is going to eventually whittle you down to like, okay, it's got to be bigger than 1.25 though, and it's somewhere in here. That's the real answer. And you'll keep checking to see if it's close. If it's close to the original number, okay? So that is a high-level idea of what you're going to be doing. Let me show you what your program's going to be calculating one by one, okay? So it's like you want to find the square root of 2. So, like, I guess the x was 2. And so you're going to make a low, and you're going to make a high, and then you're going to find the midpoint of that. Okay? So initially, for calculating the square root of 2, we're not sure what it is, but it's between 0 and 2. Okay? It's between 0 and 2, and the midpoint of that is 1. And so then we're going to check, is 1 squared close to 2? Because if that were true, then this was the proper square root. And the answer is no, not yet. We need to, like decision, guess higher. Okay? So then we do, okay, the new low was the old mid. Now we're guessing between 1 and 2. The mid of that is 1.5. And we check now if 1.5 squared is close to 2. And I think it's too big, so we guess lower. I don't know what 1.5 squared is, but we can check that really quick. It's 2.25, so yeah, that was too big. And so then we're going to change our high now to be the old mid. Okay? So now our low stays the same. We know that the square root must be somewhere between 1 and 1.5. And now our new mid is 1.25. And then we'll check if 1.25 squared is close to 2. And we're going to need to guess higher. So that is the game you keep playing. And so then the new low is 1.25, the new high is 1.5, and you can see we're getting very close. We're rapidly approaching that 1.4. So that is eventually going to get us there. And so you just play this game for a while, and this is essentially a very long loop. Okay? So that's part of your lab. That's what you're going to be doing. Okay? So that is that. That's getting you ready for the lab. I'm going to explain it some more in the lab video, of course. But that is very, very similar, don't you think, to binary search. You can just find the square root of numbers, and this is how computers can find square roots very fast. Okay, it's one way to do it. So I now want to spice things up a bit because our programs have been getting big. We've been making libraries. Consider this part of searching. You need to know about Makefiles. Okay, we've been making libraries, and those libraries have gotten big, and we have to compile everything by saying, oh man, all these .cpp files all at once. Okay, every time we change something, we have to recompile everything. So let me just go through what we've been doing, how G++ is working again, and then show you like something is wrong or something is inefficient, and then we'll make it more efficient, okay, with this thing called Makefiles. So what's happening in your program is, okay, I have a program or a bunch of them, like I have my searching.cpp, I have my main.cpp, I gotta compile those. You take those programs, you give them to the compiler, and what they do is they compile one program at a time. That's what the compiler does. It compiles first searching and then main into what's called object code, and then it links them all together at the end. So it's got like object code for searching that it's making, and object code for main that it's making, and it's bringing them together. So like here's searching, here is main, and it's going to bring them in, link them with like the C++ standard library, and then finally it builds your executable program, that you can go and run with /main or whatever. That's how compiling is working. Your compiler, it's really just translating programs to machine code, a single program to machine code, which is also known as object code. The linker's job is to combine these two files that just got compiled into different object codes. Okay? That's what the linker does, and we haven't really thought about that very much since I first explained this on like the first day of class, right? So that's what the linker does. And so, for example, if you only have just one program, like maybe you just made main.cpp, you still are probably using the C++ standard library, like IOStream over here, which has been pre-compiled for you. And so it's got to link that in, okay? So libraries definitely are linked. And then only after you compile to object code and also linked can you run your program, okay? That's the key. So that's just a review, but I want to highlight linking because I've really been saying compilation this whole time, and I really should have been saying compilation plus linking, but nobody ever really says that. Okay, so here's the problem. If we just change one file, do we have to recompile them all? Because here's what we're doing. Like if I have x.cpp, y.cpp, and z.cpp, if I just change, like I compiled these a second ago to be main.cpp, or sorry, just main. This is our executable code with zeros and ones. If I just compiled this, and I change x a tiny, tiny bit, I have to recompile them into a new version of main. So I'm gonna make a new version, I guess, down here. This is main rewritten, right? It's got 01101 or something. Do we have to do that? Like all of these are getting recompiled, every single one of them, because we're giving them to G++ all over again, and we have to. That's all we've known how to do so far. Do we have to do this is the question, and I wouldn't be telling you if we did. That is very inefficient. We didn't change Y. We didn't change Z. We shouldn't have to recompile those, because really, remember, it's going to object code first. It's compiling each of them to object code. So you got your x.o, your y.o, z.o secretly. Okay, we're going to make that O stands for object. And then those are getting linked. We don't want to redo these, because these files didn't change. That's the goal. That's what we want. So what you can do is you can explicitly tell G++, hey, wait a second, I would like you to make object files first. Do the hard part. Do the compilation part, which takes the most time. Give the -c. That is the key. And that rhymes, so maybe it's easier to remember. This -c will change your life, because what it does is you give it a single file, like x.cpp, and that will create, this creates for you x.o, okay, automatically. That's the compiled form of x, the object code for x, okay? So this is the terminal command that you give, and then it makes the object file for you, okay? That is the key. And so you only have to recompile x now. You can keep the other y.o and z.o that you had from before, because those didn't change, and you can just link them again, okay? So this -c, that is going to just compile. It will make the object file for you, and finally we get to see that, okay? G++ just did it as an intermediate step before, okay? And then, if we do this for x, y, and z, we will have made separately x.o, y.o, and z.o. That's just the custom, it puts .o at the end for you. Then we want to link them, okay? And linking, what it does is it says, it's essentially another call to G++, but what it does is just link these things together with the standard library if it needs it. That's where it brings them all together into a final thing, whatever you want to call it, like exec file name, that you can actually run. That's your final program. So that's what linking does for you, okay? Linking brings these all together. The magic of linking. And so, yeah, to link, you just have to give G++ a bunch of .o files. That's the only difference, okay? So -c for compile into object files to do the compilation process, and then give it .o files and still use -o again to make it link only, okay? Because it doesn't have to do any extra compilation. It knows that these are already object files that just need to be linked now. So that is the key. So let me show you this. Let me show you. Instead of what we had before, got like C++ -c, but with standard equals C++ 17, main.cpp. What this is going to do is it's going to make main.o. See that? And this one will do searching.cpp. That'll make searching.o. See it there? And now I can link them together. G++, I can remove main and make it again. G++, all this stuff, searching.o, main.o, -o main. This is going to link them together. And it was very fast. You could see how fast my terminal finished that. And now it made main again, and we can run it just the same. No difference. But the key thing here is, if I make a tiny, tiny difference in one of the files, like main, like cout, hi mom, I only need to recompile main.o, okay? I don't have to touch searching.cpp ever again. I'll recompile just main, and now I can relink with the existing searching.o, which I did not change. I didn't go from here to here anymore. It was already ready. It remade main, and now I have my hi mom. That is going to be key. When you have a ton of files, and you work at a large company that you're going to have a million, it takes forever to compile each of them separately. What you should do is save the ones that haven't changed. Save the compiled form of those, and that's what object files gives you. And just link them. Linking is fast. Okay, so that's the first thing. Now I want to talk to you about Makefiles, which is a way of automating this, because if you have a ton of files, you don't have to say, if you have 100 different files to compile into object files, you don't want to say G++, blah, 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 -c for all of these 100 files. You don't want to do that. That will give you carpal tunnel or something, right? So there's a better way. There's something called Makefiles, which automates this. It automates the process of recompiling. So don't be scared. I'm going to go through exactly what this means, if not in this lecture, in the next one. A Makefile it's just a special kind of file. It's a different language. It's not C++ anymore. It's the Makefile language, I guess. A Makefile is just a file on your computer, and it has to have a specific name. It's called exactly Makefile with a capital M, and what it does is it contains recipes. It's like a cookbook for how to make your programs. Okay, so here's an example Makefile. So the contents of this right here would be in a file, legit called Makefile. This is the name of it. So this is the file, that's its contents, and its name is Makefile with a capital M, no extension, just called Makefile. That's all. It's not makefile.cpp or anything, it's just Makefile. And this is what it looks like. It says, okay, in order to make main.o, I need this, and this is what I do. In order to make foo.o, I need this, and this is what I do. In order to make prog, I need these things, and this is what I do. Okay? Don't worry, I'm going to explain that extra later, but that is the high-level idea of it. And so it remembers, like, okay, this is what I need to do to make this program that I wanted. Let me go and figure out what changed and recompile only the stuff that needs to be recompiled, only the stuff that changed. That's what Makefiles can do for you. So instead of just jumping you into this kind of syntax, let me show you how to makefile a PB&J sandwich, for example. And this is what Makefiles look like. This is one rule. So a Makefile is made up of a bunch of rules, and here's an example. Maybe I should write that up here. Makefiles are made up of a bunch of rules. Here's an example rule. Okay? It says, target name, colon, that's key, then requirements, and then a bunch of steps that you need to make the target. One key thing for Makefiles is you have to tab over here. That's how it knows, like, okay, these are the recipe steps. So this is a tab character. You gotta type that. Okay, so that's tab, and here's what it says. Okay, here is us making a PB&J sandwich. If I need to make PB&J, that's what we want. What we want goes before the colon. That's the target. That's our goal, right? PB and J, I guess. We'll call it that. And then after the colon, we give requirements or ingredients, things that we need in order to make this thing. Okay? So in order to make a PB&J sandwich, I need peanut butter. I need jelly. I need bread. And I guess we can do without the plate, but we probably need a knife too, right? And then we tab over and say, okay, what do you need to do? What are all the steps that make PB&J out of these ingredients? So you're like, okay, I don't know, open PB, also open jelly, jars, and then, I don't know, get 2 slices of bread out, and then keep tabbing over, and then give the rest of your rules. Okay, so that's how you make PB&J. But the beauty of Makefiles is you can give rules for these too. If you don't have them yet, it will go and make them too. So like, I don't know, if you wanted to make your own peanut butter, here's another rule for that. You give a separate one. You need peanuts, and you need a blender, right? And then like the step would be blend the peanuts. Put them in a jar or something. Close jar. Things like that. So that's how you make peanut butter. How do you make bread? I don't know, maybe you can just take the easy way out and go to the store. Like, you need money to make bread. That's all. Money and a car. And so then you go to the store, buy bread. There's another possible rule that you could make this with wheat, right? Wheat and heat and all that stuff. But the idea is there's a bunch of different rules, and there's something that you're trying to make at the end of the day. And Makefiles will go and run all the rules for these intermediate things, if those don't already exist, and then once it has those, once it follows all the steps to make the other ingredients, then it'll finally follow the steps for the original recipe. That's what Makefiles do. Okay, so that's really it. Okay, if you just remember this kind of example, then you will never forget. Okay, so I'm not going to give you the Makefile for our current library just yet, but I will get you there in the next lecture. So yeah, here's the structure again. Its target name is really the thing that you want, and these are your requirements or ingredients. After the colon, you give them space separated after the colon, as many as you need, and then you always tab over, and then you give a bunch of, in a computer, you're giving terminal commands that you want to use to make this thing. And you can give as many as you need, because you might need several to make it completely. But usually for us, it's just one big G++ command. Okay, so this is essentially it. You give a bunch of terminal commands after this declaration of what you want and what it needs first. So the idea is Makefiles, they know when things change. So if this requirement 1 file changed and you want to remake this, it knows to rerun the rule for requirement 1. But if you didn't change this other one, it'll leave it alone. Okay, and they know how to make requirements if they don't exist yet, or if they got changed. And yeah, if anything changes, Make will only rerun the relevant rules. Like if you run out of peanut butter, it will know to only run this rule and not have to go and buy extra bread when you don't need it. Okay, so this might still be very vague, but that's where I want to leave us for this lecture. We'll be back in the next one, and I will give you a Makefile that will compile our searching library and do everything that I just did on the terminal over here automatically. All these -c things, all these -O's with these .O's. Okay, so that is where we're headed, but that is enough for now. So I will see you in the next lecture.